Welcome to another episode in which we discuss the research developed within the Applied Computing Research Group, the GCA. Now, before we jump in, we need to highlight the authors of the work we are looking at today. This deep dive covers an incredible 5-year evolutionary study authored by Raphael Z. France, Matthias H. Reben, Rodolfo Berlesi, and Fabricia Ruz-Franz from Unijuí University in Brazil.
Yeah, and it's a fantastic piece of research, really eye-opening stuff.
It really is. So for you listening, I want you to picture something for a second. Imagine a sprawling, just chaotic digital metropolis. You've got these massive, heavily fortified legacy software monoliths sitting right next to, thousands of nimble, lightning-fast microservices.
Right, like old data warehouses trying to talk to real-time serverless functions.
Exactly. Systems built 20 years ago trying to communicate with stuff deployed literally yesterday. And your job is to build a single, flawless, high-speed transit system that perfectly connects every single one of these structures without causing a massive pileup.
Which is basically impossible, right? But that is the reality of enterprise application integration today.
Yeah. Companies are just drowning in these messy, incompatible software applications. And integration frameworks are supposed to be the magic bridges connecting all of this chaos. But our mission today is to ask, what happens when the bridges themselves become too massive, too tangled, and just, too complex to maintain?
And that's exactly what this study looks at, how 4 major open source integration frameworks mutated over half a decade, and which one is actually the easiest to maintain.
Okay, let's unpack this.
Yeah.
Because we need to establish why these frameworks even exist in the first place, right?
Right. I mean, to understand the problem, you have to look at the corporate software ecosystem. We are way past the era of just getting a legacy CRM to talk to a billing system.
Right.
We are talking about enterprise application integration, or EAI. Companies have these heterogeneous setups, in-house apps, cloud software, mobile apps, all written in different languages, running on different operating systems.
So it's basically like a chaotic United Nations where no one speaks the same language, and these frameworks are acting as the simultaneous translators.
That is a great way to put it, yeah. They use this architectural pattern called pipes and filters. So the pipes are the asynchronous message channels orchestrating the data, and the filters are the atomic tasks, like, validating a payload or transforming data.
Okay, but if they are just translators, why do they need adapting? Why is this so hard?
Well, because the entire landscape of data changed. These frameworks were originally built for predictable structured routing, mapping structured spreadsheets from one SQL database to another.
Right.
But modern business demands massive unstructured streaming data. Real-time video to text, live natural language processing, complex image analysis.
Wow. Yeah.
Yeah, so when you shift from structured batches of text to massive video streams, the entire architecture of the translator has to be rewired. You're suddenly dealing with massive buffer sizes and complex asynchronous states. Adapting them is crucial, but it is incredibly painful.
Which brings us to the 4 contenders in this study, the big translators. We've got Apache Camel and Spring Integration,
Right.
which are both Java-based and very code-centric.
Right.
Then there's Mule ESB, also Java, but it's model-centric. It uses a visual drag-and-drop kind of setup.
Exactly.
And finally, Guaraná, also Java, also a model-centric visual language, but uniquely, it was born from a 6-year joint effort between academia and industry.
Yeah, it has a very different pedigree than the others.
So since adapting these tools is necessary but clearly painful, how do we actually know which one is going to cause the fewest headaches for developers?
Well, you can't just eyeball the code and say, that looks messy. The researchers used a highly rigorous scientific measuring stick for maintainability. They tracked 25 specific software metrics over 5 years.
25, that's a lot of data.
It's a ton. And they categorized them into 4 main groups: size, coupling, complexity, and inheritance.
Okay, break those down for us. Size seems pretty straightforward, right?
Yeah. Size is basically cognitive load. Number of classes, total lines of code, number of methods. The larger the code base, the more mental overhead a new developer faces.
Right, more places for bugs to hide.
Exactly. Then there's complexity. Specifically, they use the McCabe cyclomatic complexity metric. This doesn't just count lines. It measures the complexity of the algorithm by counting the number of independent paths through the code.
Like every time there's an if statement or a while loop, the paths multiply.
Yes. And it's vital to note here that Thomas McCabe, the creator of the metric, strongly recommended a maximum value of 10 for any single module.
Okay, a max value of 10. I feel like that's going to be very important in a minute.
Oh, absolutely is. Then we have inheritance, which looks at the depth of the inheritance tree and the number of children classes. Deep trees can make the code really fragile.
Right, but what about coupling? Because they looked at afferent coupling, which is incoming dependencies, and efferent coupling, which is outgoing. But wait, isn't coupling just teamwork between different pieces of code? Why is a highly connected system viewed as a negative thing here?
This raises an important question, actually. It's a common misconception. In software, high coupling means that if you pull one string, the whole sweater unravels.
Ah.
Yeah, if your routing module is deeply dependent on 50 other classes, changing one line of code suddenly breaks 50 other things. It makes testing and updating an absolute nightmare.
Got it. Okay, so we know how they measured them. So what actually happened when we look at the raw data across the 5-year lifespan? Like, how did the past versions compare to the current ones?
Well, the short answer is they all got bigger,
Yeah.
which is expected. But the scale is what's alarming.
How bad was the size explosion?
Well, Spring Integration increased its classes by 84%, and its lines of code, or LOC, literally more than doubled. It went up almost 122%.
Wow. Okay. What about Apache Camel?
Apache Camel's LOC jumped 91%. To put that in perspective, it reached a staggering 119,418 lines of core code.
Just for the core engine.
It's just the core code, yeah. We aren't even counting the external plugins. Meanwhile, after 5 years, Guaraná sat at a remarkably lean 3,504 lines.
Almost 120,000 lines versus 3,500. That is insane.
It is, but remember that complexity danger we talked about, the McCabe limit of 10.
Right, what 10 is the safe zone. How did they do?
Well, Guaraná maxed out at 8. It stayed entirely safe. But the others? Spring Integration hit 33, Mule ESB hit 39, and Apache Camel hit 64.
64.
64.
That is, I mean, that's more than 6 times the recommended maximum.
It's mathematically terrifying, honestly.
I can't even imagine being a developer trying to trace a routing error through a module with 64 different independent paths. It's like humanly impossible. And I'm guessing the coupling metrics went up too.
Oh, dependencies skyrocketed for almost all of the commercial ones. Their internal methods are just so entangled now compared to half a decade ago.
You know, it's funny. It reminds me of a Swiss Army knife.
How so?
Well, it starts out as this handy little tool, right? But over 5 years, the developers add a chainsaw and a toaster and a blender to it. And yeah, it technically has more features now, but it's too heavy to actually lift.
That's spot on. And what's fascinating here is that it points out this massive blind spot in software engineering.
Which is?
Developers are heavily prioritizing adding new features, new adapters, new endpoints, while actively degrading the maintainability of their own frameworks. They're copy-pasting or duct-taping code rather than refactoring.
Yeah, trading clean architecture for a longer feature list.
Exactly.
So we see this massive growth and tangled code, but who actually wins when the dust settles? Because you can't just look at a spreadsheet of these 25 metrics and eyeball a winner, right?
No, absolutely not. The researchers were extremely rigorous here. They ran non-parametric statistical models, specifically the Iman Davenport and Bergman-Hummel tests.
Okay, those sound intense.
They are, but they are necessary to ensure the rankings were mathematically sound globally, and not just skewed by a few massive outlier classes in the code.
Right, so it's not just a guessing game based on averages. So with all that rigorous math applied, what are the final rankings?
Okay, so Guaraná takes first place as the most maintainable by a wide margin.
Not entirely surprising given the numbers we just heard.
Right. Spring Integration actually comes in second. Mule ESB managed to improve its internal mechanics just enough to move up a spot to third.
Which leaves Apache Camel.
Buckling under its own massive size, over 1,200 classes, and extremely high coupling it, dropped to fourth place.
Wow, fourth place. But the researchers point out that Guaraná's academic roots likely helped it stay compact, right? Like keeping its depth of inheritance and number of children classes low.
Absolutely. The model-centric design and its origins played a huge role.
But wait, I have to ask. Since Guaraná is a joint effort between academia and industry, does it have an unfair advantage here? Like, is it essentially this pristine laboratory experiment competing against tools forged in the chaotic fires of pure commercial enterprise? I mean, Apache Camel has thousands of user demands driving that bloat, right?
That is a really fair critique. Commercial pressure is real. But if we connect this to the bigger picture, it doesn't invalidate the results.
It doesn't.
No, because it proves that rigorous, disciplined design can scale. Commercial tools need to look at Guaraná to realize that adding adapters and connectors shouldn't automatically mean sacrificing clean code. Guaraná uses a model-centric visual language. It dynamically assembles components so developers aren't just duplicating boilerplate code every time they add a feature. That mechanism fundamentally resists bloat better than code-centric architectures like Camel.
Okay, so it's a structural advantage, not just an unfair lack of pressure.
Exactly. And the commercial tools have to learn from that because eventually the technical debt becomes paralyzing.
Right, and that really impacts the businesses relying on them. If your framework is so bloated that adding one new feature breaks everything, it's no longer an integration solution, it's the obstacle.
Exactly. It becomes a bottleneck.
Which leaves us with a lingering thought for you to chew on today. If this 5-year trend of massive expansion and tangled code continues, what does the next 5 years look like?
It's a scary thought.
It really is. Will these open source titans eventually collapse under their own weight? Will they force the industry to start entirely from scratch with, I don't know, AI-generated, perfectly optimized frameworks?
It's very possible. The data traffic isn't slowing down, and these bridges are getting dangerously heavy.
Well, on that slightly terrifying note, we'll wrap up this deep dive. We invite everyone to listen to the other episodes and learn about the group's research projects. If you enjoyed it, subscribe to our channel to be notified when new episodes are posted.